Hello everybody, my name is Islam and I'm working at Facebook. I'm working right now at RocksDB project. I'm here today to talk about RocksDB and MongoRocks. So anybody here attended Martin and spoke about persistent cache on RocksDB? Oh, okay, so let's talk about RocksDB. So what's MongoRocks? So MongoRocks is MongoDB using RocksDB storage engine. So starting from MongoDB 3.0, MongoDB introduced a pluggable storage engine API. So we implemented the API for RocksDB, and now you can use MongoDB using RocksDB as a storage engine. So for us to understand what's MongoRocks, we need to know what's RocksDB. So what I'll be talking about is RocksDB and how RocksDB works. So what's RocksDB? RocksDB is an embedded persistent key value store. So it's simply key value store. You give it key and a value, it stores for you, and later you can ask like, what's the value for this key? It's embedded, so there is no RocksDB binaries that you connect to and do the reads and writes. It's like hashing to RocksDB and the database is part of your application. It's nice for serving workload. So if you have a machine with lots of cores, lots of RAM, fast storage device, RocksDB is built so that you can utilize these resources. It's open source, so everybody's welcome to use RocksDB and contribute to RocksDB. It's used inside Facebook by many use cases, and many services inside Facebook use RocksDB and outside Facebook as well. So in LinkedIn, it's used at least to do follow feed. In Yahoo, there's distributed key value store. Sherpa is based on RocksDB. Microsoft, we see lots of activity from Microsoft on our GitHub page, so they make RocksDB compile windows. It's also used by Netflix, Airbnb, Pinterest, and many other companies. And there's lots of engineering blog posts from this company about how they're using Rocks. So I'll talk about RocksDB architecture and how RocksDB is working. So as a concept, RocksDB is based on log structure merge trees, LSMs. So in log structure merge trees, data is stored in different files, and these files belong to different levels. So if we look at this diagram, we have multiple levels starting from level 0 to level 4. And the first thing I want to mention is almost everything in your database belongs to the bottommost level. So here it's level 4. So like 90% of your data belongs to the lowest level, which is level 4 in this case. And new updates in Delta's changes that you send to the RocksDB come from the upper levels and flow until they reach the lowest level. But basically, almost everything lives in level 4. I'm not sure what. Yeah. So let's take a look on how writes go to RocksDB and what happens when you send the key and value to RocksDB. So when we do a write to RocksDB, what happens is we add it to what we call the mem table, or the memory table. And the memory table is a write buffer. So something I want to mention is, like, in this picture, like, everything is a file, except for the mem table, which lives in memory. This is a write buffer, and everything else is a file on the storage device. So when a write comes, we add it to the mem table, which is a write buffer, and we also add it to what we call write head log. So since the memory table is in memory, so if your application crashes, you'll lose this data. So what we do is we add the key and value to the memory table, and we also append it to the write head log. So the only purpose of the write head log is if your application crashes, you can recover and rebuild your memory table. And the memory table default implementation is a skip list. We have other implementations, but the default one is a skip list. So this is the only thing that happens in the foreground when you do a write. In the background, when a memory table is full, we do a flush. So we take this memory table and create a file in level 0 for this skip list or this memory table. And this is happening in the background. So when the memory table is full, what actually happens is we seal it. We say this memory table is immutable, and we start flushing it. And we have another memory table that is being used for the foreground writes, the writes that are coming. So we talked about how data moves from the memory table to level 0, about how data moves from level 0 to level 1, or from any level to a lower level until it reaches level 4. We have a process called compaction. So when a level is full, we pick a file from this level, and we also take all the files that overlap with this file in the lower level. So, for example, if you're compacting level 1, and we pick a file in level 1 that contains keys in a key range from 100 to 200, for example, we need to pick all the files in level 2 that contains keys that fall in this range as well. We take all these files, merge them together, do the merge sort, and generate the new files that are going to live in level 2. And these two processes that we just talked about, the flush and compaction, most of them are happening in the background. And in the foreground, we only write to the memory table and write catalog. And something I wanted to mention about our files is that they're immutable. So as we saw, flush and compaction, they generate new files. But we never modify a file after we create it. So all our files are immutable. They never change. We only drop files or delete files, and we create new files through the process flush and compaction. So we talked about the LSM, how it looks like. I'll talk about how the files look like in the LSM. So a RocksDB file looks something like this. So we have data blocks that store the data of the keys and values. And we have index block, global filter blocks, distance block, some other blocks. So everything is sorted in the file by key. Inside the data block, everything is sorted, and every data block is compressed individually. So if we took a look at what we have in the data block, if we, for example, have an example like this, some keys and values, everything is sorted. What we store in the data block is we first take our input, we prefix encode it. So in this example, second key shares 6 bytes with the first one, third key shares 6 bytes with the second one. So we do prefix encoding, and of course this is very common because everything is sorted. And then we compress the data block using snappy, zlib, or whatever raglan you specify. So this is based on your the options that you use in RocksDB configuration. And this is our data block. We store it compressed. And then the index block is simply a mapping from the last key in every data block to its offset. So let's say I have a RocksDB file and I want to read the specific key. What I need to do is I go to the index block, do a binary search to figure out which data block I need to read. I go to this data block, decompress it, and do another binary search to find my key and value. We also have a Bloom filter block. So Bloom filters are a probabilistic data structure, which you give a set of keys, and they generate a low memory structure, which you can ask, do my key exist in this set or not? And they will answer with either no, your key definitely does not exist here, or yes, your key may exist here. So Bloom filters are used to, we consult Bloom filters before doing any more steps. So if the Bloom filter says your key definitely does not exist in this file, we can skip the whole file and know that we won't find anything in this file. And statistics block contain information like how many keys are in this file, how many keys are deleted, such kind of information. We also have other files. So we have the Mantis file. So the Mantis file includes information about the state of the LSM. So for example, it includes information like this file belongs to each level, and we use it to do like atomic updates to the state of the DB. So for example, when compaction runs, compaction removes some files and introduces new files. So in the Mantis, we say like these files were removed and these were introduced. We have the right-hand log with all files, and we already saw this when we are writing to the memory table. So the purpose of these are recovery. If our memory table is lost because of authentication crash, we have the log file. The log file is simply the Boolean information, so it includes like the options that you used in RocksDB when flush happens. There's some logs here saying when it happened, why it happened. When compaction runs, we have information here about like which file was picked in for compaction, or what was the output, what was the reason for running the compaction, all such information. So we talked about the LSM state and the files and the format of the file. I want also to talk about some properties of the levels. So something worth mentioning that's important, and you see why it's important, is that all the levels in our LSM RocksDB have this property that the files in these levels have non-overlapping key ranges. So as you can see in this graph, all these files have key ranges that do not overlap with each other. And this is very important because let's say I want to read key 35. In this case, I can do a binary search if I know like when I have like the range for every file. I can do a binary search and figure out that I need to check the second file to get my value, my key. So this is a property that's valid for all levels in our log structure merge tree except for level 0. So level 0 is special. Level 0 may have overlapping key range. And so as you can see here, some files have the whole like key space from 1 to 100, some files from 2 to 80, they are overlapping. So if I want to read the value for key 35, for example, in this case, I may end up, I may need to check all the files because 35 may belong to any of these. And the reason for that is, like, if we see level 1 plus, the reason for that, this is guaranteed by compaction. So all the output of all these levels are the output of compaction. So the compaction process guarantees that this property is held true for all the levels. But for level 0 files, the files in these levels are the output of flush process when you flush the memory table. So this is why we may have overlapping key ranges in our files. So if you want to do a read, for example, if you want to do a point lookup in our LSM, so what we'll need to do is go first check the memory table, and then check file by file in level 0. And starting from level 1, we need to check only one file. And this looks like lots of IOs, but it's not, because Bloom filters helps a lot to skip all the files that do not contain the keys that we're looking at. So we said that the Bloom filters are part of the file, but we try to always keep the Bloom filters blocks and index blocks in memory. So in memory, we can check the Bloom filter blocks and index blocks and figure out and go directly to the file that contains our key and value and read from the block directly. For range queries or iterators, so if we have a RocksDB iterator, if you want to scan a range, you create a RocksDB iterator and seek for your key, and then you do next to like scan a specific range. RocksDB iterator is composed of multiple iterators. So for every level you have one iterator, but for every file in L0 you have an iterator. As we said again, for a level we can do binary search and go directly to whatever key we want, but in level 0 we need to have an iterator per file. We also have an iterator for the memory table. All these iterators are combined together in a heap, and this is sort of RocksDB iterator. And in this case, Bloom filters won't help us because we're not looking for a specific key. We just want the next key. So in this case, bloom filters won't help us, but what will help us in this case to skip classify those is the fact that we mentioned earlier is almost everything belongs to level 4. Like 90% of the database in level 4. So what will help us is that the higher levels or the upper levels are, their sizes are much smaller, so they can fit in memory. So most of the time, the memory table level 0, level 1, they will be cached in the page cache. So if you won't be doing any I/O, then they will be going, all these operations will be done in memory. We also have some features in for the RocksDB iterator, which is having bloom filters for prefix. So lots of use cases have like their keys have prefix. For example, they always have the time as the first prefix of the key. So, and you want to scan a range that only have timestamp, for example, X. So we create the bloom filters for these prefixes. So in this case, you can, RocksDB iterator can use bloom filters because it can check that if this file has this prefix or not. So this was a quick introduction about how RocksDB works, reads, and writes. So what's MongoRocks again? So MongoRocks is, as I said, MongoDB using RocksDB as a storage engine. It's been in production since March 2015. It was so more than a year. It's been used in production in Facebook. It's originally built for Parse. So Parse is mobile backend as a service. So mobile application developers build their application and they use Parse to as their so Parse provides them with backend. So the data for the mobile application is stored in Parse, and the backend itself of the application is in Parse. It's one of the biggest MongoDB deployments. We have millions of collections and millions of indices. It was using MongoDB using mmap, and then we moved to MongoRocks. So when we moved to MongoRocks, we saw, of course, like huge storage savings. So it was initially 5 terabytes, and now the size is 185 gigabytes. We saw, of course, lots of improvements in our P99 latencies because in MongoRocks there's document level locking versus collection level locking in MongoDB using mmap. We have much better backups with MongoRocks. And this is something I want to talk about a little more. The backups in MongoRocks and why they're easy and why they're fast. So MongoRocks backups. So as we said, RocksDB files are used. RocksDB file, once they're created, they're never changed again. And this allows us to have like backups are now much easier to do. So our backups become much faster when we're using MongoRocks, and we're able to do incremental backups. So there is an open source tool called RockStrata, which allows you to do incremental backups using MongoRocks, and also RockStrata allows you to query your backups even without restoring your backups. So how backups work and why they're easy with MongoRocks. So let's assume we have the situation. So this is MongoRocks, this is RocksDB, but since MongoDB is using RocksDB, so this is now includes the MongoDB data. So if you want to back up MongoDB on MongoRocks, all we need to do is take the memory table, flush it to create a file in level 0, and take all this file and send them to the backup directory. And that's it. It's fast, simple. If, for example, if you're doing this on the same file system, then we just hard link these files to the backup directory, and then you can copy them to another machine or another file system. And that's it. Now you have your backup. If you want to do incremental backups, so let's say our LSM changed, so now we have some new files introduced by flush and some new files introduced by compaction. Some old files were deleted because of compaction, and now we want to take another backup. So all we need to do is figure out what are the files that are new, and these files we only need to copy these new files. And now our backup directory have all the files for backup 1 and backup 2, and we can recover for either the first situation or the second backup. And again, this is just like we only need to figure out the new files and copy them, and that's it. So this is how backups work in MongoRocks. So thank you. This is RocksDB GitHub page and MongoRocks strategy. Okay.
Question. When you did show the slide for the iterator, the search, it doesn't do meaning very, right? It just wants you to scan those files sequentially.
Yes. So the iterators are iterators are single-threaded. Iterators don't use more than one thread. Yes, that's correct. Yeah.
What is the recommended file system do you use for RocksDB? XFS, sorry.
Yeah, we generally use XFS, but I'm not sure like if there is a recommended file system specifically for RocksDB. Any system.
So I remember you guys had a program which reverse scan iterators and forward scan.
We actually had lots of improvements for previous in the iterator. So again, like our structure is optimized for forward scan. So I just want so for example, we prefix encode our keys. So when we're moving forward, we decode every key we do. But initially, when we were doing previous, we need to like it's harder because when you're moving forward, you keep decoding from the previous one. But we did lots of improvements for previous. They're not as fast as next right now. They're still slower, but like I think in the last few releases, they're 2x faster. So yeah, we did lots of improvements on previous. Yeah.
And when is the multi-threaded map table?
Yeah.
Map table will change.
Yeah. So initially our mem tables were highly concurrent on reads, but they were there was one thread that's doing the writes into the mem table. Now we have multi-threaded inserts to the mem table. So this is recent work, but now our mem tables accept our multi-threaded for writes as well. Okay, thank you.